In today's agenda, we're going to take a look at HDMI 1.3, 1.4, and 1.4a and look at what are the differences between them. We're also going to look at HDMI and see how it is related or not related to SDI. We're also going to take a peek at ancillary data and where it plays or doesn't play into HDMI, as well as look at the challenges when trying to monitor HDMI, dealing with set-top boxes, COMAC, HDCP, tablets, phones. What are the challenges some of those devices present? HDMI overview. So why HDMI? Well, HDMI was developed to reduce the number of cables between an output device and a monitor or TV set. If you think about it, you could have up to 3 video cables if you are doing either RGB or YCBCR, and you could have up to 6 audio cables if you're doing 5.1 audio. So with HDMI, the mantra was to get everything boiled down to a single cable so that it made it much simpler for the average consumer to be able to just hook up a set-top box or a output device into a TV set or a monitor, and you only had one cable that you were dealing with, and that one cable took the video in whichever format it was, took the audio in whichever format it was, and made life much simpler. As you can see on the chart, HDMI has had a steady increase in the number of devices throughout the years, with the popularity of PC peripherals and mobile devices increasing steadily. Now let's take a quick look at what is HDMI. So HDMI is high definition multimedia interface. It's a compact interface for transferring uncompressed digital audio and video from an HDMI source to an HDMI receiver. It can be used for any types of video formats, from standard def up through 4K with conventional connectors. It can also support up to 8 channels of audio, either compressed or uncompressed linear PCM. HDMI also makes provisions for the use of HDCP, which is the high bandwidth digital content protection for doing encryption of the content data. As stated in the previous slide, HDMI can use HDCP to encrypt the signal if it is required by the source device. The content scrambling system is a digital rights management system for encrypting the source data being sent to the receiver. There are 5 different types of HDMI connectors: Type A, B, C, D, and E. Type A is the standard HDMI connector found on the back of most monitors and TV sets. Type B is rarely seen. It is a 2 TMDS link or dual link HDMI cable for super high resolutions in excess of 4K. Type C is just a smaller version of Type A. Type D is the micro version found on many cell phones and tablets. Type E is a new connector for automotive applications or any application that may require the connector to be held in and snapped into place. It has a retention clip on it, much like an RJ connector has. A HDMI transmitter has 3 TMDS links from the transmitter to the receiver and a TMDS clock channel that convey the audio and video from the transmitter to the receiver. There is also a EDID HDCP channel for reading the EDID ROM of the receiving device so that the transmitter knows what displays resolutions are supported. There is a CEC, or Consumer Electronics Control Channel, for controlling the devices. And then there is a reverse Ethernet reverse audio channel that can be set up between the receiver and the transmitter. The HDMI signal is a TDMS signal for the video going from the source to the receiver. The TMDS is a transition minimized differential signaling. The goal was to try to reduce the number of ones and zeros that would reduce the overall bandwidth that appeared on the cable, so we could have longer cable runs with lower bandwidth effectively on the cables themselves. The DDC channel is used to communicate from the source, request the EDID data from the receiver, what its maximum resolution and color space is, as well as communicate some of the HDCP data between the receiver and the transmitter. The utility line is used for reverse Ethernet and return audio that we'll talk about in more detail a little bit later. There's a HPD, or a hot plug detect. So every time you plug in an HDMI cable, that signals the transmitter to go request the EDID data from the receiver, so it knows how to set up for that particular receiver, because it may be a completely different receiver than was just last plugged into it. And the CEC line is the Consumer Electronics Control. That allows devices that when you turn on a particular player, it can communicate across the CEC and actually turn a monitor on. Or if you do some particular changes in a monitor, that can actually reflect back to the transmitter or the source. HDMI 1.4. There's a new data channel in HDMI 1.4 that HDMI 1.3 did not have. This new data channel is used for reverse Ethernet and return audio, going from the monitor TV set back to the source or the set-top box. Also, 1.4 provided for 3D support from Blu-ray players. HDMI 1.4a extended the 3D by adding side-by-side and top-bottom support for over-the-air broadcasts from cable companies, satellite companies, and the like, where we have to do frame packing within a single frame, and then the monitor will do the expansion and the showing of the left channel or showing of the right channel in the proper order. There was a change in the cable from 1.3 where we added one more wire so that we could get a differential pair for the reverse Ethernet and return audio channel that 1.3 did not have. There is no physical change in the cable from 1.4 to 1.4a. One of the unique things that we have found, though, is even though this extra cable is not required for the support of 3D, only for the support of the return audio channels, most set-top boxes look for that pair, since that extra wire was added at the same time that support for 3D was added. So rather than trying to query a set and do parsing, a lot of set-top boxes just turn around and look for the presence of that extra wire being terminated between the source and the monitor to actually indicate that the device is capable of handling 3D. So you must have a 1.4a style cable for 3D to work correctly in almost all situations. So if we look at HDMI 1.4 with the return Ethernet channel, so the changes from 1.3 to 1.4 are that in 1.3 and earlier, if you had devices that required required internet connectivity, you had to either wirelessly or wireline have Ethernet run to each one of those devices independently, as well as those devices connected to the monitor, and possibly even Ethernet connected to the monitor itself. 1.4 solved the issue and stayed with the mantra of trying to keep the number of cables down to a minimum, i.e. 1, between a monitor and an output device. So all you need to do is provide Ethernet to the monitor, and when each individual input is switched up, it will send the Ethernet back down to the device that is providing the video. And in that manner, each device then gets its Ethernet through the HDMI cable and is switched up. And you don't have to have the individual cables or the individual Ethernet on each device that way. Likewise, the audio would be backfed to a device if you were doing a web service from the TV and you wanted the 5.1 actually out your speakers, but yet your TV was the device logging into the web service. It could provide the audio back to your 5.1 surround system to play out multi-channel audio, as well as for use with webcam data. HDMI 1.4 also provided for both UHD and 4K resolutions at 30 Hertz and below. So this is in keeping up with the higher and higher requirements of the consumers wanting higher and higher resolutions available in their living rooms. Now let's take a look at how HDMI compares to SDI. HDMI signals. So the video portion of the HDMI signal uses transmission minimized differential signaling, or TMDS. This is a technology for sending high-speed video and audio data from a transmitter to a receiver that is used in HDMI and DVI interfaces. The transmitter incorporates an algorithm that reduces the electromagnetic interference over copper wires by using both differential signaling as well as the transition minimized, or keeping the number of ones and zeros all across the transmission path to a minimum. In the HDMI, it also carries the video, the audio, and ancillary data in one of 3 modes. We have video data periods for all the video data. We have data island periods and control periods. During the video data periods, the pixels of the active video are sent from the transmitter to the receiver. During the data island period, which occurs in the horizontal and vertical blanking interval, the audio and auxiliary data are transmitted over these series of packets. The control period occurs between the video and data island periods for control of the devices. This transmission format, from an overall look, is very similar to what we do in SDI, where we have EAV, SAV, and ancillary data in both the horizontal and/or vertical intervals. But as we'll find out in a few slides, there's quite a bit of difference after that point. So when we look at a sample frame of HDMI, it looks a lot like SDI from a structure standpoint. We have our horizontal interval on the left-hand side, we have our vertical interval above the picture raster data, and then we've got all of the lines of our picture raster data. In the horizontal interval, we do have our data island periods where we do send the audio data. In the vertical interval, there are data island periods, but the data within those data island periods have nothing to do with the types of data we would send in the vertical interval of SDI data. We'll take a look at what some of those differences are in the next few slides. With the TMDS channels, the video that's carried across will be in one of the three different formats across each one of the TMDS channels. If it happens to be RGB data, then the data is carried straight across as blue, green, and red across 0, 1, and 2 channels. If the data is 8-bit YCBCR data, it is also carried as CBYCR data on TMDS channel 0, 1, 2. If the data happens to be YCBCR 422 data, then the transmitter uses a channel pack type of approach where it packs the data in the three channels in a very unique arrangement. A HDMI transmitter must be capable of producing RGB and either YCBCR 422 or YCBCR 444. Since a transmitter could use either 444 or 422 YCBCR, a receiver must be capable of taking all three formats in. Also, HDMI has the ability to support 8-bit, which is mandatory. It can support 10-bit, 12-bit, or 16-bit deep color if needed. Part of the video data encoding consists of taking the 8-bit transmitted video, presenting that to an 8B, 10B lookup table, and converting the 8 bits of video data to a specific 10-bit word via a lookup table. That data is then looked at and either XOR'd or XNOR'd depending on which method will produce, again, less number or the least number of ones and zeros. That data then is presented to an inverter. The inverter will look at that data and the surrounding data and invert this particular packet if that will further reduce the ones and zeros across the transmission line. The receiver has to do the inverse function that the transmitter did. It gets the received data in, looks if that data was signaled as being inverted, reinverts the data if it was, presents that down to either the inverse XNOR or XOR circuit as indicated in the original data. Then that data will be presented to the 10B, 8B inverse lookup table to convert the data back to the original 8 bits of video data that the transmitter started out with. The aux data or ancillary data used in HDMI is somewhat different than what we're used to in SDI. The listing on the page shows the different types of data that is carried within the data island periods. The AVI info packet indicates the resolution of the video and the coding structure, either RGB or YCBCR, to the receiver. The audio info packet indicates the presence of audio and whether that audio is linear PCM or one of the supported compressed formats. The AVI info packet and the audio info packet are both required for proper operation of HDMI to receive audio and video from the transmitter to the source. HDMI and closed caption data. In NTSC, we're used to 608 captions being carried on line 21 of the actual video itself. In HD-SDI, the captions are carried as data packets in the vertical ancillary data space. 608 is buried inside of the 708 packets. In MPEG, the 608 are actually on an actual visible video line encoded with the video. In 708 captions, it is carried in the user data in the header of each picture start code. HDMI itself actually knows nothing about captions. It is the job of the set-top box or the DVD/Blu-ray player to overlay the captions on top of the video and present it as burned in or embedded captions to the receiving device. HDMI with content protection, or HDCP. There are three main parts to HDCP within HDMI. The AKE, which is an authentication key exchange, happens between the transmitter and the receiver. And the transmitter will query the receiver, which is the handshake portion, and the receiver will send back its key to the transmitter, which will allow the transmitter to send its key to the receiver so that they can now decrypt the incoming video. They also included a key revocation list. The key revocation list is in newer receivers and the newer standard, where if a receiver has been deemed to not play according to the standard, or the body that makes that receiver, the company, they can actually be removed from being able to display HDCP data. So newer receivers or newer transmitters have a list of older devices that have been kicked out of the party and are no longer allowed to decode the video. Now let's take a look at test applications. How do we test devices that use HDMI? One of the biggest issues we have is dealing with non-HDCP compatible receivers talking to an HDCP enabled transmitter. When a non-HDCP receiver is connected to a transmitter, the transmitter asks for the key in the handshake exchange. The receiver does not respond. Within about 3 to 5 seconds after that absence of an exchanged key going from the receiver, the monitor, back to the transmitter will shut the video down. One of the things that we have found is that if you have a HDCP compliant source, the compliant source does not shut off its HDCP. It does not look back at the content to see if the content was DRM'd or not. It costs about 20 bucks more in parts and a fair amount of intelligence to actually look back at the content to see if the content was HDCP'd or not, or digital rights managed. So if a set-top box, a Blu-ray player, has the capability of playing DRM'd material, which a Blu-ray player does, it always turns on HDCP. So you could actually take your own home movies, burn them, put them in a Blu-ray player, play them out, and they will come out HDCP'd on the output. That's the issue we've got in the broadcast community when we're trying to deal with looking at or taking HDMI devices and actually convert it over to SDI. HDCP keeps getting in the way all of the time. And we need to know about this and know how to handle it and what to do when this happens. And what to do is basically is not a lot. If the device puts out HDCP, you're not supposed to break it. So how do we see the output of an HDMI device, a set-top box, or an over-the-top device? We need to have an HDCP compliant monitoring device. If we want to see the output of a set-top box and just be able to view the waveforms in a waveform monitor, the waveform monitor must be an HDCP compliant waveform monitor. If we want to look at our web content of an OTT transmission, over the top web application, The cell phone or tablet must also be hooked up to an HDCP compliant waveform monitor in order to be able to see the output of the video and the audio out of those devices. Also, if we want to test the performance of a transcoder or an encoder application, we would need a device that is capable of being able to look at the client device and be able to hook up the HDMI to the quality analyzer and be able to look at the actual video quality. The Tektronix PQA600A is a HDMI compliant picture quality analyzer that can actually look at the quality of the video being returned from a client device. If we want to look at the output quality of a set-top box, for example, we would need to have a picture quality analyzer that is capable of being an HDCP compliant device and handshaking with the HDCP transmitter in the set-top box. We would also need to do the same if we wanted to see the output of a cell phone or a tablet, as mentioned in the previous slide. If, for example, you wanted to see the output quality of two different Blu-ray players against each other, we would likewise need a compliant device receiving the data. With the picture quality analyzer, if you lay the original data down onto a Blu-ray disc, play Blu-ray disc in player A, we can come up with a score of the quality of player A's output. We can put the data in player B, play that data, score that data, then compare the score from the Blu-ray player A against the Blu-ray player B and actually look at the upconversion and scaling algorithms in both devices and see the quality of the output from both player A and player B. If we wanted to verify the performance of a set-top box, we would need to feed our reference stream to an encoder, have that encoder go through our network, be delivered to the set-top box, the HDMI output of that set-top box, then loop back to the picture quality analyzer to record that data to be compared against the original reference that was sent to the encoder and get the MOS score for that particular output. This could be used to compare different encoders against each other or different set-top boxes, quality of scaling and output quality within the picture quality analyzer. For doing basic set-top monitoring, you can use the Tektronix WFM 5250. It is a waveform monitor that has two HDMI inputs. Both HDMI inputs are HDCP compliant. It will monitor audio loudness for COMAC quick checks. It'll look for black or frozen frames, give you valid or invalid color gamut, and also has an advanced error logging capability with a full web server UI for control of the device. It also has two SDI switched inputs so that you can do side-by-side comparisons of a SDI source to its HDMI converted source and do side-by-side in the box comparisons of the SDI source against the HDMI source. If the HDMI input is non-HDCP encrypted, it will also produce a HDMI to SDI conversion and give you the SDI out from the HDMI input if the HDMI input was non-HDCP protected. Looking at the screens off of the waveform monitor, the video session screen will tell you what the effective input signal is, whether it's YCBCR or whether it is RGB, tell you the colorimetry, the measured format, whether the output or input was HDCP'd or not, and then also tell you the status of the signal as far as gamut compliance for RGB, composite, and luminance, and record those off into a log file for further investigation if needed. With HDMI, we don't always know what is coming out of a device unless we have a way of looking at it, especially with a device that is HDCP protected. In the case of the screenshot I have up right now, this is one of my media players, and if you look at the top left corner tile, you'll see an RGB trace, and you'll see that all three, red, green, and blue, are actually lifted off of black. This is as close as I could get them with adjusting the contrast and or brightness controls within that media player. So I could get nice dark grays, but I couldn't actually ever get full black out of this particular media player. If you look in the top right hand side, you'll see the ancillary data that was present and being sent, that the AVI info packet was there, the source product description packet was there, as well as the audio info packet. And at the top of the screen, it's actually a decode of the product description, the particular player I was playing out of. In the bottom right-hand corner, you'll see the colorimetry that this was playing out at 1080p at 5994. The signal was RGB 444 8-bit, and the colorimetry was 709. If you look over to the input and output status, so the input was HDCP'd, and I had it plugged into one of my monitors, my TV sets, and that was also an HDCP compliant. Since I took this screenshot off of the web UI and the input was HDCP'd, we are not allowed to even put a screenshot out of the particular picture. On the waveform monitor itself, it did have full picture decode, but we're not allowed, due to HDCP compliance, to even let a thumbnail of that picture go out the door. If you look at the bottom portion of the video session screen on the right hand tile, you'll also see that we can look at the color correctness, the RGB gamut, the composite equivalent gamut, and the luminance gamut of the signal, and actually record and log off the errors. The waveform monitor also has a running error log that is date and time stamped, as well as time code, if time code happened to be in the information you were running, if you needed to go back and look at this data at a later point in time. In this slide, we're looking at the output of a device that was producing color bars. And if you look at the color bar, especially at the top, you look at the red and the magenta, you can see that the red and magenta are substantial ways away from their target boxes. Without having a device that can either look at HDMI, and especially if it was HDCP'd, you'd actually have no idea that you are producing an incorrect color representation of the original data going in. So it can be very handy to have a device that can look at it, and then you can go back and figure out, was it something in the original recording, was the playback device wrong, and do some investigation and troubleshooting as to why we were getting incorrect color representation out of our particular device. On this slide, we were looking at the output of a set-top box from a vendor that was producing 1080p 5994 RGB data, which all looks correct until you look at the color imagery that was actually being sent. The color imagery that was being sent was set to 601, which is the color imagery for standard def TV. The video was indicated correctly, but the issue is that all receivers that I have tested, at least to date, if you put HD data into them, they make an assumption that the data is encoded in 709, not encoded in 601 space. So they turn around and decode it in 709 and make the corrections and the assumptions from 709 color space. So when you present 601 video, even though it was indicated in the HDMI stream that it was 601, the receivers never looked at it to actually decode it as 601. They all decoded it in 709, and hence the picture was completely washed out and looked really, really bad. On the WFM 5250, we can also look at the EDID that we send to the transmitter. The EDID is a 256 byte hex dump. There is a parsing table provided with the device if you need to turn around and parse out what the data actually states that is being sent to the transmitter. Now we're going to take a look at set-top boxes, the COM Act, and what happens with set-top boxes when they are hooked up to TV sets and sending either the Dolby AC3 to the set-top box or sending linear PCM out from the set-top box to the receiver. We can do audio monitoring also with the WFM 5250. We can look at the audio output of a set-top box being presented to a TV set. We look at this audio as linear PCM because linear PCM is the only audio that is actually processed by the set-top box. All digital audio is just passed straight through a set-top box and never touched. Linear PCM is produced in the set-top box from the compressed audio being fed to the set-top box. So the set-top box is actually doing audio processing when it produces a linear PCM output. We can look at this decoded output and actually run up to 30 hours of loudness logging within the WFM 5250 product. Within the audio monitoring, there is also an audio session screen. The audio session screen will look at each channel individually, whether it's a 2-channel or a 5-channel multi-channel output, and tell you if you've had any clips, overs, mutes, silence, what the active LKFS is of each individual channel, what the LKFS is on any paired channels, and what the overall loudness is of the entire audio package being delivered to the TV set. It will also look at the channel mapping, where each channel is and how the channels are being derived and being delivered to the TV set from the set-top box. So in summary, HDMI usage is on a steady growth path in PCs and in mobile devices for video. HDMI is a source receiver negotiated resolution, not the same as SDI, where SDI is a feed-forward resolution. HDMI quite often uses HDCP as its content protection. With HDMI with HDCP, it can present several challenges for testing the quality of your video. With HDMI, you really do not know what you have until you actually look at it and see what the device is actually producing. Tektronix offers a range of products for testing HDMI with HDCP, from picture and video quality testing to waveform monitors, where we can compare side-by-side SDI against HDMI inputs. We can look at the audio quality, we can do COM-ACT monitoring, do spot checks on HDMI outputs. With the SDI HDMI picture quality analyzer, we can evaluate the quality of your video and give you a MOS score of the actual received quality. It enables subjective evaluation of your content with side-by-side wipe swipe style displays where you can sit and look at your uncompressed right next to your compressed received video. I hope you've enjoyed today's presentation on HDMI. We will now take a few moments and field a few questions from the audience.